Okay, in this question, we're given that the population of cats in a large garden grows according to the logistic model, and they give it to us, where t is the time in weeks. And then there are several questions here. I would like to answer all of them by looking in general. Instead of looking at n of t here with numbers, we notice those three numbers. In general, they change from question to question. What you get is a function like this: constant over 1 plus constant e to the negative constant t. So there are three constants here, and t is the variable, time. So usually, for questions like this is the time, and n is the number or the population, if you'd like, depending on the question, of course. Let's say in this question it's the population at time t, and depending also on the question, they tell you the time is given in weeks or in years or in days, depends on what you're studying. But in this case, we have A, B, C, D, E. We will solve actually all of them in one shot. But in order to do this, we will spend like a couple of minutes talking about logistic growth in general. So the formula for it is given here, where, of course, in many cases you need t instead of x, so you can replace this with t safely. Everything else is the same. And there are important points to know about the logistic function. Once you see any question that has this function in it, know that this is a question about logistic growth. And in this case, there are specific answers to it. For example, this c that you see here, the constant that you see on top, is the carrying capacity. It's the highest possible value. So y equals c, when you arrive at it, your graph can never touch this line y equals c. It gets very close to it, but it never touches it, telling you that your population cannot be more than this constant c. So maximum possible population, if you want. This is the maximum possible population, is the number here, c. Good. It's good to know from the beginning that this is the case. Okay, and then remember it's given in terms of t, but I'll keep it as x here. Then when you put time 0, if you put it in the formula here, put 0 instead of t or x, then x here, of course, is 0. 0 times anything is 0. E to the 0 is 1, and 1 times anything is that thing. So it will be this here, c over 1 plus a. You see, c over 1 plus a is what's left when you replace x by 0. So all of this becomes 1 again, and it goes away. That's verified now. So the initial point, the initial value of the population, to get it, you just put c over 1 plus a for any logistic function written in this way. Okay, good. And another thing is that as x or t goes to infinity, or in this case x goes to infinity, we know that the function or the population f of x, or if you want, if it's a population n of t, must go to c, to the carrying capacity. C here is the number that's on top. That's the maximum possible. Always look for this number. It's the maximum possible. If you want to know, I'll go back quickly and tell you. From this formula, I know that maximum possible number of cats is 345 immediately, because this is the carrying capacity, maximum. And also, initial, when you put t equals 0, this goes away, and you have just 345 over 1 plus 14. So you can compute this. This would be the initial population of cats. If you want, let's do it now. So it is 345 over 1 plus 14 equals 23 cats. Good to know. So 23 is when you replace 0. So 23 cats initially. initially, and n of infinity, you know, as t goes to infinity, is 345. This is cats, is the maximum possible. It cannot exceed it. That's the maximum possible. These things you can get immediately just by looking. Imagine. So I will leave it now and go back to this to remind you of one last important thing, is that you see the graph is increasing. It reaches, this is the initial point, and look, it's increasing and concave up, but it reaches this point here and it changes its mind. It becomes increasing but concave down, and then it starts following this horizontal line and it never touches it. So now it's concave down. This important point here is called the point of maximum growth, or in business this is called the point of diminishing marginal revenue. Not necessarily revenue, it could be profit also. Marginal returns, better to say. Returns. So diminishing marginal returns. The point at which the derivative starts behaving differently. So up to the point of diminishing returns, the function is increasing and concave up. But after it, it's increasing still fine, but concave down. That's telling us something about the rate of growth of this function. It's saying that when it reaches this point, it reached already the maximum rate of growth that it could ever have. And even though it continues to increase afterwards, but it's increasing at a decreasing growth level, okay, until it becomes almost horizontal with time. And eventually, the maximum that you could have is the carrying capacity, which is the number that you can always read on top in the function if it's written in this standard way. Okay, good. And the important thing about this point here, that the coordinates are things that you can compute. This point of maximum growth or diminishing returns, it will always be, and let me write this down, this will always be, you will do at time t equals ln of a over b. Always the point of diminishing returns have t coordinate, or the first coordinate, ln a over b. It's very important to remember this. It will never change. So always you go to your function, locate a, let's use a different color, locate a and b, and then from them you can do the point of diminishing returns will be at t equal ln a over b. Get it from the a and the b that you have in the formula very easily. And then the y coordinate, it's telling you, will be half of c, exactly in the middle between the x-axis and the c, y equals c. In the middle, c over 2, we have our point of diminishing returns. Okay, so I'll go back just to make things look better. Okay, let's take not everything, just most of it away. And now we have studied it in careful detail, kind of, but still, to solve questions about it, you need one more thing. You can always come back to this picture to remember everything that you need to know about logistic growth. So one last thing before we solve our question is that if you want to do the inverse of this, so if we have y or t, let's say n of t equals, or n, let me just make it easy. If n, the population, equals constant over 1 plus a e to the minus b t, then what I want is for you to tell me what is t in terms of big N. Solve for t. So solve for t. Okay, so let's see. To solve for t, first thing I'll do is cross multiply. So n times 1 plus a e to the minus bt equals c. And so now you're looking for t. Remember, always remember, your aim is to get t. So divide by n both sides. You'll get 1 plus a e to the minus bt is c over n, which means a e to the minus bt is, subtract 1, c over n minus 1, and this will be c minus n over n. Okay, and then you can divide by a. Divide by a, you'll get e to the minus bt is c minus n over a times big N. And now this means that e to the bt, if you take the reciprocal, because it was power negative, so now if you do 1 over this equal 1 over that, 1 over this is e to the bt. Now 1 over this will be an over c minus n. I just took the reciprocals to get rid of the negative that I have in front of the b. Remember, we are clearing the way for t. At the end we need t. So e to the bt equal, I'll write it from here, e to the bt equals, what was it? an over c minus n. an over c minus n. And so apply ln now. Ln of this side equal ln of that side. So it will be ln of e to the bt equals ln of an over c minus n. Good. And finally bt will come down. This is property of ln, and ln e is 1, so this will be bt equal ln of an over c minus n. And finally, therefore, t is 1 over b ln of an over c minus n. Perfect. Now look at this formula. This is the inverse formula. The inverse what? Inverse logistic formula. Very nice to know this formula. So we will highlight it and tell you what does it do. It asks you to give it a number or a population, a specific population, and it will tell you the time at which this population will be reached. You know, in the regular function, they give you, you input the time. So for you, the time is your input. And what is your output for this is the population, because n of t will give you, when you put t in this formula, it will give you n. So you're getting n from t in this case. Okay, but the other formula was what happens if you if you have the specific t. This is you have it. Suppose that you have it. You have the day, and you want to know what would the population be on that day. So this way you can find it. So in the other way is, what if you have the population n, this, let's say that you are thinking of it, and you're thinking, what t do I put here so that the answer is going to be a specific one? Let's say will be 300. What should I put for t so that this will be 300? You will see a question like this. So now we will start answering all of these questions. Let's do them one by one. This thing that I did at the beginning of reviewing the logistic model is important. So always refer to it before you solve questions like this, so that you remember the process of it and where do these points come from. So now, initial population of cats, immediately you'll say this is at n of 0, which is 345 over 1 plus 14. Because in this case, you know, in this one, A is 14, B is 1.5, and C is 345. This is if we write it in our standard way. the standard way is what? Just to remind you, it's C over 1 plus A e to the minus bt. The standard way of writing the logistic function n of t equal to this. Okay, so now you have this number, you find it on your calculator. So what's this number? 300, I found it already, 345 over 1 plus 14 equals 23 cats initially. Good. And then second one, let's do it with another color. How many cats are in the garden after 1 week? This means n of 1 is what? What is the number of cats after 1 week? So you'll do the formula here. E to the power minus 1.5 and then the t that you give it. You know, if you give it t equals 0, it will give you 23 cats initially. Now you give it after 1 week equals, as a decimal. Yeah, so after 1 week, 345 over 1 plus 14. Yeah, after 1 week, we have approximately 84 cats. Is 83.66, which is approximately 84 cats. From 23 to 84 in 1 week. Now, how long does it take for, now we go to the next question and put a different color, let's say this, and the question is, how long does it take for the cat population to reach 260 individuals? So this is what? This is the number of individuals. N equals this, and they're asking you, how long does it take? So what is the time? Remember in the previous questions, here they were giving you the time. This is t is given, and they're asking you how many. So what is n of t? That was the unknown. T is the given, n of t is the unknown in parts B and A. But in part C, it's given to you that 260 cats are there, and they're asking you, so how long did it take for them to reach 260 if this is your formula? So you just go back to what we did here, the inverse logistic formula, and say the time will be 1 over B times ln of an over c minus n. And let's take this part and copy it. So I'm going to put it here. This is the formula. So just keep it for our reference. We will just keep it here. Okay, so this is the formula for this question. And go back in the video to watch how I computed this t. The easiest thing is to have the inverse function. So now you say, this t that you're asking me to do is 1 over b. Notice in the question we have a and b and c. So 1 over b, which is 1.5, ln of an, so 14 times the n that they're giving us here, 260. 14 times 260 over what is it? C minus n now. C is 345 minus n, which is 260. This was the inverse formula. I did it in general, and so it's much better that you watch how I did it in general, because every time you will have to do the same process. So it's easier to just do it in general. So 1 over 1.5 times ln of a fraction. So this fraction is 14 times 260 over 345 minus 260 equals, so as a number 2.5. So 2.5 approximately weeks. It means after 2.5 weeks you expect there will be 260 cats in the garden. Notice this 260, you can change it. You say in general, if you want to know after how long would you get a specific, you just replace it in the formula. You see, the formula tells you here that all what you need to do is give me this n. A, B, and C are constants. You get them from the function already. So the only unknown here is n. Give it to me. So, for example, you say, I want to know when it will reach 100. how many weeks does it take to reach 100 equals, it tells you 1.2 weeks approximately, so a little over 1 week. So to reach 200, for the population to reach 200, then you need almost 2 weeks, exactly 1.97, so 2 weeks. So to reach 260, that was the question, to reach 260 you will need 2.5 weeks. And notice, to reach the maximum, which is 345, you cannot even put it because the denominator now will be 0, so it will be like infinite, cannot do it, infinity. So it's telling you at time infinity I would reach 345. It's like it's the maximum that I could ever reach. Nice to know this. And what is the maximum cat population that can exist in the garden? Immediately 345 from the formula. You say it's C equal 345 cats, where this C is the one that you get from the function. N of t is C over 1 plus a e to the minus bt. The C is the one that I have in this formula. Let's use this one. Yeah, this is the C that you write here. And we saw in our example it is 345. Good. That's the maximum number of cats that can be in the garden. Okay, and the last thing is, when does the point of diminishing growth come into play and how many cats will be present then? So remember, the point of diminishing returns happen when, or diminishing growth happen when you have ln A over B. So this is ln, and now what was A for our function? It's 14, and B is 1.5, remember, 14 and 1.5. So ln 14 over 1.5, and this will give me the time at which I have the diminishing growth. So ln 14 over 1.5 equals, so as a decimal, yeah, so approximately at, let's say approximately here, approximately t at 1.76 weeks. So 1 week and 3/4 of a week. You can say 1 week and 5 days if you want. So this is like 1 week plus 5 days, like 12 days altogether. Okay, so like 1.76 times 7 equals 12 days almost, yeah. So in any case, at 1.76 weeks, we will have the maximum growth rate for the cats. Okay, and to check that this is really the inflection point, the right point, so therefore the point will be t, comma, c over 2. This t is the ln A over b. Okay, so this point, ln A over b with y coordinate c over 2 will be 1.76, comma, c over 2, the maximum, 345 over 2. What would that be? 345 over 2, 172.5. So 172.5 here, 172.5. This will be the point of diminishing growth for this cat population, where the first one is the number of weeks. So after 1.76 weeks, so it's like 1 week and 5 days, the number of cats then will be 173. You know, if you put the right, if you want the right interpretation, you'll have 173 cats, and at that point will be the maximum growth rate of the cats. And this, I will show it to you in Dismos. It's important that you watch this. Okay, so let's write the function 345 over 1 plus 14 e to the power, where is the power? Yeah, negative 1.5 x we'll use. Okay, and now let's go there and watch it. Look at this. This is the logistic growth that we have for the cat population. And remember, we said many things. First is that at time 0, we have how many cats? 300. Remember, 23 cats, I remember. Yeah. How did we get 23? Just you remember, you replace 0 in the formula, so it will be 345 over 1 plus 14. And that will give you the 23. Good, that was this point. And then the maximum y equal 345 is the line at which, let's make a dotted line. Okay, and this is the maximum that maximum cat population that you can have, 345 in this garden. And also, what else? They asked us the question is, when will it be 260 cats? Look now as I'm moving, you want the y to be 260. So 50, 60, yeah. You see at 2.5, yeah, around 2.5. And that's when we said in 2.5 weeks you will reach 260 cats. So see here, it was after 2.5 weeks we will reach 260 cats. It was on the graph. Okay, and what else did we do? The point of diminishing growth is when you have ln of A, so ln of 14 over B, so B is here is 1.5, remember, comma, C over 2. C is 345 over 2. And label it. You see that this is the point of diminishing marginal returns, or in this case diminishing growth for the cat population. Before it the function was concave up, and after it concave down, and the function is always increasing. As you can see, logistic growth is always an increasing function, but before the point of diminishing growth it's increasing and concave up, so the derivative is also increasing, so it's increasing at an increasing rate. But after the point of diminishing returns, it increases at a decreasing rate. That's why it's concave down after this point. Okay, this is nice to see. And one thing that I will do here is draw the derivative for you, so you see why we say diminishing growth. So I will do the derivative of this function, 345 over 1 plus 14 e to the minus 1.5x. Look, and we'll give it another green. Let's do it in green or red. The derivative is red. Look at this maximum of the derivative. It's exactly at the point of diminishing growth, 1.759. You see, it's the same x coordinate or t coordinate. So it's telling you that the derivative of the logistic function, so the logistic function is the blue, its derivative is the red. And you see that the derivative is maximum exactly at the inflection point of the logistic growth. So if you do, for example, x equals ln A, which is 14, 14 over B, which is 1.5, you will pass through, and because this is a line that you make it dotted better, okay, then you see that both points pass through it. So the maximum of the derivative and the inflection point, of course, they are related. That's why it's an inflection point of the blue, because it's a maximum of the red. The red is the derivative, and inflection points, you get them from derivatives of derivatives. So as you can see, because it's a maximum of the derivative, it will have slope 0. And if slope of the derivative is 0, it means that the second derivative is 0, and that's why you get an inflection point. Very nice. So this is kind of a review also of logistic growth in general. And let's see, did we solve everything now? Yes. So when does the point of diminishing growth come into play? You say after 1.76 weeks. So after 12 days, you can say it comes into play. And how many cats will be present? You will say, of course, you cannot say 0.5. You say 173 cats will be present then. Present at the time of diminishing growth. Diminishing growth. And notice that this number here always equals C over 2, approximately, where C is the carrying capacity. So 345 over 2, you get 172.5, which approximately is 173, because the context is about cats, and these don't come in fractions, they come as whole numbers. And I will stop here.